Hello everybody, we're ready to start Unit 2 on derivatives. This is the first of 2 units on derivatives. Today we're talking about rates of change and tangent lines. I'm going to start looking at things we know from geometry and previous courses. Recall that a tangent line was tangent to a curve at a point. Now, a secant line would intersect in 2 places, but a tangent line would intersect a circle at 1 point. We want to look at how that's related to calculus. In this example, there's a 4th degree polynomial, and line PQ passes through that polynomial in 2 places, both at point P and at point Q. So the line PQ is a secant line on that curve, but the point Q is not a tangent point, whereas point P is tangent to the curve only at point P. So in calculus, we want to be sure that we understand that you can intersect a curve at another place along the curve and still be tangent to the curve in a very small neighborhood, say around a specific point. And we're going to use that idea to help us find the slope of a curve at a specific point. That's the idea of the slope of a tangent line, or what we're going to call as the instantaneous rate of change, which is also known as the derivative. And there's 2 really important points to recognize here. When I have that point A, f of A, that point shares 2 things in common with its tangent. It shares the point of tangency, and they share the same slope at that point. So really important idea. You know already how to find the average rate of change. The average rate of change is the slope of the secant line. Slope of the secant line. We say that that's the change in y divided by the change in x. And we've looked at stuff like that since Algebra 1, pre-algebra. Let's find the average rate of change for this cubic function over the interval from 1 to 3. So we would need to have the f of 3 and the f of 1. So if we substitute 3 here and subtract 9, we're going to end up with 18. We need the f of 1, doing the same thing, 1 cubed minus 3. And then we can find that average rate of change, or the slope of the secant line. The slope of the secant line by simply finding the f of 3 minus the f of 1 divided by the change in the x's, 3 minus 1. So 18 plus 2 divided by 2 is 10. Our average rate of change on that cubic is 10. The instantaneous rate of change, that's a little bit different. So if we wanted to find the slope of the tangent line using that slope formula, it's going to cause division by 0, and it's going to leave us with 0 over 0 because the change in y would be 0. The change in x would be 0. We call this indeterminate form. Not allowed to do that. So we need plan B. And plan B is going to do this. We want to know the slope right at some point A. So we're going to add a little bit to A. Now imagine, if you will, that this is just really zoomed in. If I found the slope of the secant line from A to H, and then moved that line closer and closer and closer to A, so that my interval is getting smaller. Eventually I could be so close to A that the slope, I could find the slope of the line that way. And if you think about it, you saw in Unit 1 what we called the difference quotient, f of x plus h minus f of x divided by h, the change in x. So this goes away. We called this the difference quotient, f of a plus h minus f of a divided by h. So we could do that and actually calculate the slope of the tangent line by moving that line closer and closer to A. So are you hearing limits there? Couldn't get away from limits, could we? So let's apply those limit rules to that rate of change. And as we let h approach 0 or get infinitesimally small in a really tight neighborhood, when we evaluate the limit in that very, very small area, allowing the h values to get so close to 0 that we've almost got 0 over 0, but not allowing that to happen, we could have an estimate and find the slope of the curve at a point using the limit process, as long as the limit exists. That's the big idea, using the difference quotient and the properties of limits. That's the big idea to finding the tangent line or the derivative. Now, here's 4 examples. I'll do one, you do one. We're just looking first at using the notation properly. So the f of a is 1 divided by 2a, and the f of a plus h is 1 divided by 2 times the quantity a plus h, and that's sufficient. So you do this one. The f of a is 3a minus 2, and the f of a plus h is 3 times the quantity a plus h minus 2. On C is the f of a is 2a minus a squared, and the f of a plus h is a little more complicated because we're going to substitute and distribute 2a plus h minus a plus h quantity squared, and then distribute 2a plus 2h minus a squared minus 2ah minus h squared. That's for part C. Then for part D, you have 3 divided by a plus 1, and then f of a plus h is 3 divided by a plus h plus 1. So that's pretty good practice just for using the notation correctly. And let's say we're given the graph y equals x squared, and we want to use the difference quotient to find the slope of the curve at the point 3, 9. So you think about the parabola that's going up like this, and we get up here to 3, 9. And graphically, what they're asking us to do is to calculate the slope of that line that shares the point 3, 9. What's the slope of this line? My tangent line. And I can find that using that difference quotient. And that difference quotient said we wanted to find the limit as h approaches 0 of a plus h, the f of a plus h, minus the f of a divided by h. And this is my function f. So we're going to find the limit of x squared as we let that term go really close to 0. But this can't be x, it's got to be a. So we want a plus h minus a squared. So distributing, we have a squared plus 2ah plus h squared minus a squared divided by h. And simplifying, collecting like terms, you notice that each term remaining has an h in it. If you factor out the h, we can get rid of that division by 0 that way. And now I'm at a place where we can apply that limit property. You notice that I left the limit notation until I'm ready to use the limit notation, just like any operation. So the operation is to substitute 0 in place of h. And that way we know the slope of that line to a, that's the slope formula for any x value on that parabola. We found a general formula. We'll say this is the slope formula for any value of x on the parabola x squared. But they gave us the point 39. So at the point 39, the slope is 2 times the x value, because this is my a and this is my f of a. So our slope is 6. The slope of the tangent line, or the slope of the curve, at the point 39 is 6. This slope is 6. So now that we know that slope, can you write the equation for that line? To write any equation for any line, you need a point and you need a slope. So we can do that. Notice the preferred formula in AP Calc is going to be point slope form. So the equation for my tangent line is y equals the slope times x minus 3 plus 9. That's the equation for the tangent line at the point 3, 9 on the parabola x squared. So anytime you take the limit of the difference quotient and your limit produces unbounded behavior, like positive or negative infinity, then we know that the line x equals a is a vertical tangent line on the graph. And those are going to happen when you get something like a 0 on the bottom and a number on the top of a fraction, right? Or you get some huge number and some tiny, 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 tiny decimal. It's going to either send you to positive or negative infinity based on the sign of those numbers in that kind of a thing. There's also normal lines that we'll talk about, and a normal line is just a fancy way to say perpendicular. Some textbooks will say normal lines, some textbooks will say orthogonal. Orthogonal is another way to say perpendicular. Orthogonal is perpendicular. Normal is perpendicular. What do we know about the slopes? The slope of one line is perpendicular to another line when they're opposite reciprocals of each other. So let's explore this graph. F of x equals 1 over x plus 3. We want to use the limit definition and compute the slope of the tangent line at some point A. So again, that equation, sorry about that. That formula is the limit as h approaches 0 of 1 over a plus h plus 3 minus 1 over a plus 3, that entire thing divided by h, which is a little cumbersome, so let's clean that up a little bit. We can pull the 1 over h out here and get a common denominator for the two fractions. How about a plus 3 minus a minus h minus 3 divided by the common denominator, a plus 3 times a plus h plus 3. Okay, cleaning up the top, you have a minus a and 3 minus 3. Then with only negative h in the top and a positive h out here, we could take out that h and that h. It's going to leave us with a negative 1 in the numerator. And using the leftover terms, now we can apply the limit definition. So the slope, substituting 0 here, the slope is going to be negative 1 divided by a plus 3 quantity squared. So that's what they were asking us to do. Use the limit definition to calculate the slope of the tangent line at some point A. Now, if we carry that forward onto B, I can find the slope of the curve when x is negative 1 by substituting negative 1 into our formula. If this is my A value and we were left with negative 1 over a plus 3 quantity squared, then our slope is negative 1/4 when a is negative 1. And notice they're asking us to write the equation of the tangent line and then write the equation of the normal line. So not only do I need the slope, down here the slope of the normal line is going to be opposite of negative, so it's going to be positive, and the reciprocal of 1/4 is going to be positive 4. But I also need to have an x and a y value. And the function we said was 1 over x plus 3. So if we substitute negative 1 right here, our y value is 1/2. And using point slope formula, the tangent line is the slope times x minus our x value, negative 1, plus 1/2. And then the equation for the normal line would look exactly like the tangent line, but have a different slope. So 4 times x plus 1 plus 1/2. And then the next idea, I want to draw you a picture here. If we had x is negative 1.1, you think about the equation, and you know that there's a vertical tangent line over here at negative 3 on that graph, 1 divided by x plus 3, and there's a branch up here, and there's a branch over here. And if we come to negative 1, we know what that tangent line is. It's sharing that common point. And then we want to look right here at negative 1.1. We can't find this value without putting 1.1 here, but I want to find the value on the tangent line just to get an estimate. That's what it's good for. So I want to do f of negative 1.1 using the tangent line that was negative 1/4 x plus 1 plus 1/2. Let me move my graph here. Plus 1/2. Whoop. 0 first. Plus 1/2. And checking all of that on my calculator, I find out that the number is 0.525. Okay? So it's close to the actual value, and if you wanted to know the actual value, you could put negative 1.1 plus 3 and calculate that number, which turns out to be 0.526. So you can see how incredibly close we are. It's just this number is on the actual graph itself, but the estimate on our tangent line here was a little bit of an underestimate since the branch of the graph was concave up and the tangent line was underneath the curve. So it's just a good estimation tool that we can use when we have the tangent line. So here we are at the end. This is kind of a you own it, let's summarize what you did. So we're going to use a calculator to evaluate the average rate of change of the secant line, the slope of the secant line, between the point 1 and 1.001. So it's so close together. We're going to find the slope of that secant line. So with my calculator, I want to substitute, I would just put the function in, 4x minus x squared, and then I would just let the calculator do the work here. I'm going to write it out. 1.001 minus 1. And my calculator gave me the answer of 1.999 as the average rate of change. So we had a very small neighborhood between just 1,000th of a unit away from 1. So close to the slope of the tangent line. But this is an average rate of change. Then we want to look at a different average rate of change more generically using the 1 and the f of 1 and 1 plus h and f of 1 plus h. So calculating that average rate of change, that's the slope of the secant line. My function was 4x minus x squared. So 4x minus x squared, and then I'm sorry, and then we're going to substitute 1, 4 times 1 minus 1 squared, and divide that by h. So this is the x plus h. See our new x, we're putting 1 plus h and 1 plus h. So if you think about it, this is the 4x minus x squared, and this is the 4x minus x squared using the 1. So cleaning that up, whoop, and distributing the 4, we have 4 plus 4h, expand this and subtract, minus 1, minus 2h, minus h squared, and 4 minus 1 is 3, so minus 3 divided by h. This is the slope of my secant line. 4 minus 1 is 3, and 3 minus 3 is gone. 4h minus 2h is 2h minus h squared divided by h is our slope of the secant line, or average rate of change. Each term has an h in it. If we factor out the h, you can divide away that common factor, remove that 1, and we know that the average rate of change is 2 minus h, provided that h is not 0, right? H can't be 0. Then the slope is 2 minus h. So what happens to the secant lines between the points 1 and f of 1 and 1 plus h and f of 1 plus h as h goes to 0? Well, you hear the limit there? What happens as we allow h to go to 0 for that average rate of change? Then the slope is 2. That's what happens. As h goes to 0, our slope goes to 2. Slope of the tangent line. And then to finish it up, how do you find the general formula for the slope of the tangent line? At any point using x and f of x, and then x plus h and f of x plus h. That's the difference quotient using the limit for the definition of the derivative. So when I take the limit of the difference quotient, that gives me the slope of the tangent line by finding the limit of f of x plus h minus f of x over h. And we're going to use our function that was 4x minus x squared. That was our function. So let's do this process to finish up our lesson. So the derivative is the limit as h approaches 0 of 4x plus h minus x plus h squared minus 4x minus x squared, all divided by h. And that limit is 4x plus 4h minus x squared minus 2xh minus h squared minus 4x plus x squared divided by h. And everything with an x should cancel out, so we can factor an h from the numerator. So 4 minus 2x minus h divided by h. Eliminate that division by 0 and apply the limit. So if we substitute 0 into the remaining term, our derivative, which is the slope of the tangent line for any x, is 4 minus 2x. Lesson 1. We're all done. See you next time.